let's have a closer look on how we can visualize fluid flow. That's a bit complicated topic, and there's not one perfect solution. There are many different small solutions that we can use for this visualization. And that's also a topic where we are working at scientific projects here at HTWSA. Yeah? We want to make fluid flow visible to see if our experiments, if our calculations are right. What can we do? Yeah, we can visualize it by streamlines, by pictures, by numerical simulations, or we can make smoke visualizations. We can use paint on the wall, or what's even always a good hint about fluid flow is when you have somewhere dirt. For example, if you have dirt at the car or dirt or dust on the wall, it gives you a hint about fluid flow. Okay, but it's always an indirect measure. Yeah, why do we want to visualize it? Or how can we visualize it? I tried to make an easy example. Here's a sketch of a pipe elbow. We have fluid flow from here. It goes into this elbow region and comes out here. And what happens if we have fluid flow in such an elbow? We will have a pressure drop. That's important if you want to build heating tubes or pipes. Yeah? And we will have turbulence regions. We have regions where we get swirls inside this pipe. And that's something we must examine because it's always bad if you lose too much pressure over this elbow. This is a schematic sketch, and what I tried to give you some visualization. And how have I done it? I built an experiment, and maybe it's in this movie not so good to see, but please download the slides or look into the slides, and here you see some water flowing through this elbow region. And what can you see? You see that here I injected some ink, some color, and with this ink, with this color, it was possible to see the turbulence, to see the swirls inside the elbow. This was my first experiments. I built it on my own, and maybe it was not so professional, so I tried to build one more. And this is the second step. This is the second elbow example. I built it more in a better way, or more advanced, and with a more detailed geometry. And then I had the problem: should I use ink? Should I use color to visualize the flow? It's a bit difficult to do this, and it's also not so good to see it. So I decided to find another way, and I used an infrared camera to visualize the heat. And then I just injected here cold water. I injected here hot water into this region, and now it was really good to see the fluid flow of the hot water into the cold water, even if when I did the experiment you could not see it with your eyes, because hot and cold water both are invincible. You don't see it. But if you use an infrared camera, you can see the different temperatures. And there I got some really good methods to make a visualization of fluid flow for you. And also here's a small picture about this problem. made with numerical simulations. Maybe we come to this task later. Okay, here again, same picture, and you can also find this picture on YouTube. I don't want to start the movie now, but you can try it on your own. Go to the slide, click to the link, or scan this QR code with your mobile phone, and then you can see what I did in this experiment. Another way is, sounds really simple, but is done really often in technical applications. For example, that's the geometry of a car. I think it's a kind of BMW. And you can see they glued small, really small filaments of wool onto the geometry, and now if the air comes, you see the direction of the air on the surface. Here it goes into this direction, so all the wool filaments will go in this direction, and behind the wheel you have some swirls. So, or for example, this part here. That's a mirror of a car, of the left side of the car. And what the engineers did here, they took a serial model of a car. I'm not sure what it was, maybe maybe a Mercedes, and they put color, white and blue color onto the surface of the car, and then they had a high velocity of air here from this side, and then you see regions of turbulence and regions of laminar flow around this car geometry. Yeah, why do we do this? What can be developed in future? Yeah, all the geometries we have now, the airplanes, the cars, they are not optimal. No? They are not so bad, but we can make further developments. For example, here in aircraft technology, we had this winglets at the side of the wings. That's a relatively new development, and it prevents the rolling of swirls over this plane, and it makes the wing much more efficient. And how did we get the idea about this winglet? It came from nature. Here we see a condor, the big bird, and he also has winglets on his wings, and he uses it to optimize the fluid flow around the wings. Here we see also this airplane with a winglet and an airplane without a winglet, and we see it was the same method. They put some ink, some color on the wing, and then they used it, and then they can see the different fluid flow behavior. Or for example, that's another picture. Now, maybe it's also not so good to see on the movie. It's detailed geometry of a turbine, of a steam turbine, and also inside the steam turbine geometry, you have to optimize the geometry, you have to find the right geometry to get a better efficiency of the turbine. And how can you do this? You can make computational fluid dynamics simulation, you can make theoretical estimations, or you can make experiments. And here they put also some red and blue color into the turbine. They used it, and afterwards they could measure where the fluid goes and where the swirls occur. Here also, it's also a picture of a wing of a turbine. Yeah? You see this red color, it occurs on the blade of the turbine, and you can see how the fluid flow behaves. And then the idea behind it, you can change the geometry a bit, optimize it, and then you have less swirls and more efficiency of the turbine. Or for example, development of ships. Building ships is a really old science. We do this for thousands of years. Even the Greek or the Roman people developed ships, or the Vikings, and they did it in a really good way. And if you deal with ships, building ships, optimization of ships, you always have the problem of fluid flow of water around the hulks of the ship. And you can also make numerical simulation where you can optimize the ship's hulk here, or experiments. Here you see the bows or the tail of a ship, and they also use, I think they used some ink, yeah, they used some color to visualize the streamlines over the ship's hulks and to optimize it. Or that's another example. It's an example from my life as a Bosch engineering. It was a small organic Rankine cycle turbine. We built it in the pre-development department. And here you go really close to the picture. If you look on the slides, you can see the streamlines that were built by the fluid flow by a dirt trace. Yeah, you had some oil into the turbine, you get some particles, we get some soot and smoke, and they built a streamline at the housing of the turbine, so we can get an estimation about fluid flow. And what I did, I also made a computational fluid dynamics simulation of this geometry, and I placed the result of the CFD over the turbine geometry, and it fitted really well. Okay, let's go a bit faster. Here we have an experiment with a car in a wind tunnel, and it had a velocity of about 15 kilometers per hour. And here they used smoke filaments, yeah, small smoke particles in the wind tunnel to see how good the geometry of the car was optimized. That's another case, yeah, at another company. Here it's from Volkswagen, from VW, but it's the same examination. They put here this Audi or this Golf car into the wind tunnel. They made different stream trays to visualize the fluid flow around the car and get estimation of optimization of the geometry. Or here, it's another example. That's optimization of a spoiler. And here you see they also made experiments in the wind tunnel with the smoke method, and they got swirls here behind the car, and so they could optimize spoiler geometries of the car. Well, that's even an interesting and nice visualization. Here you can see an airplane, and when I showed you the winglets before, the developments at the winglets at the end of the wings, you could see that we get a really big swirl at the end of the wing. But normally, if you have a normal plane, you cannot see this because it's invisible. But here, same, that was picture from the 1950s, and what they did, they sprayed some powder out of the airplane, and then the airplane flew through this red powder, and so it was possible to make a good picture of this swirl behind the wing. Or for example, this picture here, that's a ball in water, and depending on the velocity of the water, the fluid flow can be laminar, where you see this laminar swirls behind the ball, or the fluid flow can be turbulent, and then you see much faster swirls behind this ball. Now that's another example. Here again we have a wing and swirl, and we see here a lift off of the fluid and induction of the swirl. Really nice picture. Or here a cone with swirl. Okay, that's another method to make it visualization better, yeah. And even if you have such swirl pictures, yeah, if you make smoke pictures, you can use these pictures to get information about the velocities. Or, I told you, you can also make numerical simulations. Here are some results of numerical flow behind a ball. But if you do numerical simulation, we should always do kind of validation and compare it here with this experimental setup too.